All right, welcome everyone. So today we are studying longest common subsequence. It's a common dynamic programming algorithm. It's also available in the Q&A book under the as around the problem number 63, so you can find it there as well. Okay, so the problem is very easily defined. It's called the longest common subsequence. We're given two strings, S1 and S2. They're both on the same alphabet. It could be alphanumeric, for example, A through Z, 1 through 0, etc. Or it could be some other alphabet as well. And we want to find the common subsequence, not necessarily contiguous, that appears in the same sequence in both the strings S1 and S2. That means we can skip letters, or we want to find the common sequence here. For example, if you're given two strings, networking and frameworks, we want to find a common subsequence such as EWORK. It exists in the same sequence, not contiguous in the first word. It's coincidentally contiguous in the second word, doesn't have to be. And the length of this longest common subsequence is 5. So that's what we want to find. Such a problem has a lot of applications. It could be used for file comparison, data compression, DNA sequence alignment in bioinformatics. And so in general, it has a lot of applications, very easily motivated problem here. So how do we solve it using the dynamic programming? If you recall, in dynamic programming, the main thing that we have to often start with is the notation. So let's suppose the string S1 is of size N1 and S2 is of size N2. They don't have to be equal. So we can say that LCS S1 I S2 J is the length of the longest common subsequence of S1 that starts at index I and S2 that starts at index J. Okay, so that's how we have generalized this particular LCS call to be. Now, if S1 and S2 are well understood, we can simply drop them and we can just call them as LCS IJ. In fact, that's a notation we'll continue to follow, assuming that these strings S1 and S2 are understood from the context. Now, of course, what we are really interested in is LCS S1, 0, S2, 0, because we want to find the common subsequence not imposing any other considerations. So this notation meets the two requirements of the dynamic programming notation that we have discussed in the past, that it's comprehensive, it can handle solution and subsolutions, and it's quantity focused, not necessarily solution focused, even though the question might have been posed to us, what is the common subsequence? We're just focusing on the length of the common subsequence here, assuming that we can always reconstruct the actual subsequence, as we'll discuss a little bit later as well. So as is common, many times we focus on the recursive formulation first before we're talking about optimality. So let's talk about step 3 first before we talk about step 2. You can kind of go in any order, but sometimes it's more interesting to talk about recursive formulation right after you talk about notation. So if you have LCS IJ, as you can notice here, now we have dropped S1 and S2 from this notation. So LCS IJ, we can observe that if the first letter is the same, S1I is equal to S2J, so the first letter that's within our available sequence, then we will simply take 1, counting that common character, and compute LCS I plus 1, J plus 1. That's the condition listed over here. And if they're not the same, then we will say, okay, the first characters don't match. Either in the first string we won't use that, or in the second string we don't use that. So that essentially becomes maximum of LCS I plus 1, J, or LCS I, J plus 1. And that's the simple recursive formulation. With that recursive formulation, we can easily prove the principle of optimality here. The principle of optimality is an easy observation that if LCS IJ is optimal, then LCS I plus 1, J plus 1 must also be optimal for that subsolution. Otherwise, it would contradict the optimality of LCS IJ. Similarly, if this is not this case, the other case, still the similar proof by contradiction can be established as well. So in this case, all that's left for us to do is to come up with the bottom-up traversal of this particular algorithm. We can write a simple base case. We can say for I is equal to 0 to n minus 1, or for j is equal to 0 to n2 minus 1. If S1 n1 minus 1 is equal to S2j, we would set LCS is equal to 1, and we can assume that LCS is an array that's initialized to 0, and it goes LCS n1, n2, so it's an n1 times n2 array, as we can easily observe here. In the recursive step, all we have to do is we just have to kind of calculate from I is equal to n1 minus 2 down to 0. That's because that's the way our recursive formulation has been defined. So we want to compute the higher values of I first here. So then that's all we would do. We would say S1I is equal to S2J, just like we said in the recursive formulation. We would say LCS IJ is equal to 1 plus LCS I plus 1J plus 1. And going by the sequence that we have established here, the base case that we have established here, we would have definitely have computed LCS I plus 1J plus 1. So we can see here, this is simply a double loop here. So it would take n1 times n2 time. This takes n2 time, this takes n1 time. So overall, n1, n2 time dominates. And that's really what we have here. It's a problem with the numerous applications, and we can solve it in n1, n2.